Welcome,
Okay.
One
Sorry.
World Fractals and session. And our first speaker is Xavier Tolsa from Barcelona, and he will going to talk about the dimension problem of harmonic measures. So please.
All right. Well, thank you for the invitation. So it's a pleasure to be in this seminar. So let's start. So I start defining harmonic measure and introducing some notation. So in all this talk, omega stands for an open and connected set. That's a domain, and most of the time will be in Rn+1, right? So this is the ambient space. And then for a point P in omega, omega super P stands for the harmonic measure in omega with pole in P. Essentially, well, roughly speaking, modulo technical details for a set E in the boundary, the harmonic measure of E that with pole in P is the value at P of the harmonic extension of the characteristic function of E to omega. And so harmonic measure is a notion that is essential to understand the Dirichlet problem for the Laplace equation, and also plays an important role in many problems in complex analysis and potential theory. So then we are interested in the metric and geometric properties of harmonic measure. For instance, when harmonic measure is mutually absolutely continuous with respect to n-dimensional Hausdorff measure, typically, we can think that typically omega has a finite surface measure of this form. But although in this talk we'll talk also about domains with fractal boundaries and with non-integer dimension. All right. Then, what is the connection with rectifiability also of harmonic measure? This is another interesting question. And recall that a set E is called n-rectifiable if it is almost everywhere contained with respect to this n-dimensional Hausdorff measure in a countable union of C1 or Lipschitz n-dimensional manifolds. Another important question in the area is what is the Hausdorff dimension of harmonic measure? And recall that the dimension of a measure, or like such a harmonic measure, equals the infimum of the dimensions, Hausdorff dimension of the set E with full measure, right? So this is full measure. And we assume that omega is connected, and then assuming that omega is connected, then the dimension of harmonic measure does not depend on the precise pole P that we take, because all harmonic measures are then mutually absolutely continuous. All right, let's start with some we'll review some classical results in the complex plane. The complex plane is special because it is very well known that harmonic measure is invariant by conformal mappings. So one can use complex analysis to study harmonic measure. Some classical results are this, for example, the Ries-Brothers theorem from 1916 that asserts that if we have a simply connected domain, with whose boundary is rectifiable in the sense that it has finite length, then in this case, harmonic measure and dark length measure are mutually absolutely continuous. Much later, in 1985, Makarov showed that if omega is simply connected, then without assuming, of course, this condition, without this, then harmonic measure has dimension 1. He has a more precise result, but for us, for the moment, this is enough. Jones and Wolf in 1988, they showed that for any open set, arbitrary open set in the plane, harmonic measure is at most 1. The dimension of harmonic measure is at most 1. And in 1993, the result was sharpened by Wolf, who showed that, in fact, for any domain, there is a set with in the boundary with sigma finite length, which concentrates the whole harmonic measure. And well, what happens in higher dimensions? Well, the analog of Riesz-Bader's theorem. Remember that this is the theorem about simply connected domains with whose boundary has finite length. And the analog is false; it does not hold. And there are counterexamples in the two directions by Wu and Zimmer. And about what happens about the dimensional harmonic measure. Well, it's almost trivial that the dimensional harmonic measure should be between n minus 1 and n plus 1 in Rn plus 1. The n minus 1 comes from the homogeneity of the fundamental solution of the Laplacian in Rn plus 1. All right. And one should expect, by analogy with the case of with the plane, that the dimension of harmonic measure is at most n in Rn plus 1. Because in the plane, the dimension is at most 1. But this is false. In fact, Wolf showed in 1995 that there exists a snowflake-type domain such that in R3, such the dimension is larger than 2. And well, this example can be extended to generalized to higher dimensions quite easily. And well, in the converse direction, Burgen showed that the dimension can never be n plus 1. That is, in Rn plus 1, the dimension for any open set, the dimension harmonic measure is at most n plus 1 minus some constant epsilon n that is positive and depends only on n. And then a natural question is, what is the sharp value of this constant epsilon n? And well, this is very open. This is not known. Jones' conjecture is that epsilon n is equal to 1 over n, and this is based on this harmonicity of this function, but when G is harmonic. But there is very little evidence of this conjecture. And in fact, there is so little evidence that, for instance, in R3, the conjecture is that epsilon should be 1 over 2. But for instance, Badger and Genshaw, they have calculated this epsilon n that they have obtained a bound for epsilon sub 2 in R3, that this is this number that is very far from 1/2. This calculation comes from the methods of Burgen. It's essentially a quantitative, a more quantitative proof or argument than the one of Burgen. All right. Let's mention some results in codimension 1 were in Rn plus 1. So then codimension 1 is n. In this case, well, this codimension is special because the connection with rectifiability. This is an integer dimension. And well, a basic result of Dalberg from 1977 asserts that if omega is a Lipschitz domain, then harmonic measure is an A-infinity weight with respect to surface measure. In particular, it is mutually exclusively continuous with respect to surface measure. And more precisely, in fact, it satisfies a reverse Helder inequality with an exponent 2 in this density here. All right. There are many other results in codimension 1 from the PD perspective, for example, that study the connection of the behavior of harmonic measures with the Dirichlet problem and the geometry of the domain. But the only thing that I will mention is in codimension 1 is this result, this theorem obtained by Azam, Hoffman, Martin, Maybroda, Murgoglu, myself, and Wolberg in 2016. And this asserts that if omega is open in Rn plus 1, then if we have a subset of the boundary with positive and finite length, so this is a subset and arbitrary, well, I guess that Borel, and we assume that in this subset, harmonic measure and surface measure are mutually absolutely continuous, then in this case, the set must be n-rectifiable. Well, let's say that this result solves a question posed by Bishop in the 1990s, and it's proved using the connection of the Riesz transform with the Green function, and using the L2 boundedness of the Riesz transform, and using the fact that the L2 boundedness of the Riesz transform implies rectifiability. Well, just recall that the Riesz transform of a measure, such as this is harmonic measure with polarity infinity. So the Riesz transform of this measure is the integral of this kernel. This is the Riesz kernel, the gradient of the fundamental solution of the Laplacian in Rn+1 with respect to this measure. And it turns out it's not difficult to check that this Riesz transform equals the gradient of the Green function with polarity infinity. And then this is the reason or why Riesz transforms are useful in the study of harmonic measure, right? Because the Green function has a direct connection with harmonic measure, and then via this identity, one can relate Riesz transforms and the behavior of Riesz transforms to the harmonic measure. All right, but now let's focus in the case of codimension non-integer, different from 1. And first, the case of codimension is smaller than 1. All right, so in codimension different from 1, or different, smaller than 1, that is, we are in between some dimension s between n and n+1. Well, in this case, harmonic measure does not behave typically like Hausdorff's measure. And precise result is this one, is a joint result with Jonas Assam and Michalis Murgoglu. And it asserts that if we have a number S in this interval, and an open set omega, and a set E in the boundary with finite Hausdorff's measure is dimensional. And we assume this condition that it's the called CDC condition, it's capacity density condition. I will say in a moment what means this. Well, if it turns out that if omega and this Hausdorff's measure are mutually absolutely continuous, then this can only happen when these measures are 0. So, except in a trivial case, these two measures, harmonic measure and this Hausdorff's measure, can never be mutually absolutely continuous. Well, let's say that this result was obtained by Assam and Murgoglu in the case of uniform domains that I will, it's a class of special domains that I will not define, and in more generality by myself using different ideas. And what is the local CDC? It's a kind of thickness of the complement or thickness of the boundary, typically. One says that the local capacity density condition holds in E if for some radius R0 positive, we have that the capacity of the ball minus omega is bounded from below by some constant times the radius to the power n-1. And this must hold for all x in E. Typically, one asks this for in the boundary, but this is a local condition, so we ask this for all x in E and for radius small enough. This capacity, essentially, you can think, for the purposes of this talk, that it behaves like a Hausdorff's content of dimension n-1, essentially. But this is not true, but let's say this. Assume, but one can think this. All right. Another result that is more connected to the topic of this talk is about what happens with the dimension. We have that in this same case when we have S in this interval, and if we assume that the boundary is S-alpha regular, which means that we have this condition here, the Hausdorff's S-dimensional measure of any ball intersected with the boundary is comparable to the radius to the power S. for all x in the boundary and all radius up to the diameter. In this case, it turns out that the dimension of harmonic measure is always strictly smaller than S. So this is, and this phenomenon is the so-called dimension drop. It means that the dimension of harmonic measure is smaller, strictly smaller than the dimension of the boundary. When this happens, we say that there is dimension drop for harmonic measure. All right. So we know that this happens for these domains, and this was shown by Jonas in 2018 as Jonas and but let me say that previous results by Batakis, Volberg, Makarov, and Zunik and others have been obtained for self-similar Cantor sets and other sets of dynamically generated in a sense. Well, the proof of Azam uses blow-up arguments and other techniques using from the result of Bourgain that I have already mentioned. In particular, it uses this lemma. This lemma says that if we have a set that is S-alpha regular and some measure omega on E, this could be a harmonic measure or another measure, then if for all x in E and all radius up to the diameter there exists some ball by rho with y contained in this ball intersected with E, and the radius rho is comparable to the radius r. In fact, it should be smaller than r and not much smaller. So that this is the S dimensional density of this measure on this ball. So if we have in this ball by rho, we have that this S-dimensional density of the measure is much larger than the S-dimensional density of in this other ball, or the opposite, that it is much smaller for some m. So this must happen for some m large enough. Well, in this case, we have that that the dimension of the measure must be strictly smaller than the dimension of the set. All right. And what happens in the case of codimension larger than 1? That is, we are in this interval, in n plus 1. That is, we consider again a set omega open with S alpha regular boundary. And then the question is if there is always the dimension drop. And this was asked by Wahlberg some years ago. And there are some results that seem to confirm this. For instance, this is true for Cantor repellers. This is true for limits, for some large class of limit sets obtained by, limit sets of conformal iterated function systems. This is a result by Urbansky and Zunik and another class of, and also for large classes of self-similar Cantor sets. So in these cases, there is dimension drop, but there are some hints that this could also fail. For instance, long ago, Batakis showed that if the set is, the boundary is not alpha regular, then we may have the dimension of harmonic measure can coincide with the dimension of the boundary, in this case. And also Chris Bishop, he showed that not only dimensions could coincide, but also harmonic measure and Hausdorff measure could be mutually absolutely continuous without the alpha regularity. And in fact, it turns out that the answer to Wolber's question is negative. This was shown by David Jesnak and Julia in 2023. They showed that for S small enough, that is between 0 in the plane, for S small enough from between S between 0 and 0.25 essentially, there exists an S alpha regular set, in fact contained in a line in the plane, that harmonic measure for the complement is comparable to Hausdorff measure on the set, S-dimensional Hausdorff measure in the set. And in particular, of course, the dimensional harmonic measure then is equal to S. Well, and let me say that this example is constructed by it's a perturbation essentially of a similar Cantor set. So this example of David, Jesnak, and Julia could not be so similar because this would contradict results of Batakis, for example. But instead, the way they constructed this example was by perturbing a self-similar Cantor set. All right, and what happens if S is not so small? For instance, in the plane, assume that S is, for instance, between 1/2 and 1. All right, then it turns out that in 2024, I showed that in the particular case, when we have a set that is for regular and contained in a line for this range of S, then we have dimension drop. So, that is when S, I repeat, when S is in this interval for large enough, then we have dimension drop. Well, let's say that for subsets of C1 curves, we have the same result. And in higher dimensions, there are analogous results replacing the 1/2 by n minus 1/2 in n plus 1. Well, and then another question is what happens for regular subsets of lines in the plane for this, for instance, in this case. So this case is not covered by the examples of counterexample of David, Jesnak, and Julia, and by my result. Or even, and then also what happens for subsets that are not contained in lines or hyperplanes when we are close enough to codimension 1. All right. So so in the last 5 minutes, what I will describe some results when we are close to codimension 1. That is when we have some S between some n minus epsilon and some n in Rn plus 1, and we are at least when we are talking about sets E that are S-alpha regular. All right. Then to announce these results, we introduce this coefficient. This is a bilateral beta infinity. This is defined in this way. This is given an x and an r. This coefficient this coefficient. This coefficient is equal to infimum over all. Sorry. This coefficient equals the infimum over all n planes L of the Hausdorff distance between E and this ball BXR, and then here we put the n plane L and intersection with the ball BXR. So this measures how far E is from some hyperplane inside this ball BXR in a scale invariant way. And here we have the coefficient beta 2 that is equal to this infimum over these n planes. But here this is an infimum in terms of L2 norms. So here we divide by this measure of the ball, and we integrate with respect to mu, this distance square. And this is not a bilateral coefficient, but it's unilateral, because we measure how close is the set or the support of the measure to be contained in some n plane, so that this beta 2 does not detect holes, let's say. These coefficients appear in the theory of uniform rectifiability. All right. Well, in 2020, Jonas Azam showed that if we have a set in Rn plus 1 that is compact and has S-alpha regular boundary with some constant C0, and omega is the complement, then if we have that these bilateral coefficients are uniformly large for all x in E and all radius, then there is some sorry. Then there exists some epsilon depending on this delta here and on this constancy 0, such that for S between n minus epsilon and n, we have dimension drop. That is, if we have this, we have dimension drop if we are close enough to n. All right. And much more recently, in a joint work with Jingjing Kai, I showed we obtained a quantitative version of this result of general sum. In this result, we show that if we're in the same situation where we have a set E in Rn plus 1, S a post regular, and omega is this set, and we have, but now we assume the beta 2 coefficients larger than delta. Then there exists some constancy depending on the CDC. The CDC is a weaker, remember this stands for capacity density condition. This is a weaker dependence than the one from C0. The C0 from the alpha regularity, C0S. Then if S is between n and this n minus C delta square, then we have dimension drop. So this looks a little stronger than the bilateral beta, bounded from below, but in fact, also we have another version of this result, well, another version around a related result that asserts that if we have the bilateral betas larger than delta, then there exists some constancy depending on C0 such that if S is between, in the case of the plane, sorry, now we're in the case of the plane, if S is in this range, then the dimension, we have dimension drop. All right. And well, if instead of the plane we are in Rn plus 1, then the delta square that we had here is replaced by this delta n plus epsilon in our result, where for an arbitrary epsilon larger than 0. In this case, we have dimension drop. A couple of remarks, and I will finish. Is first that previous quantitative bound was obtained by Richard Patak some months ago, and instead of having dependence of power type like this one or this one here, he had an exponential type of dependence on delta. Let me say also that just to explain a little which techniques we use. Well, the techniques that we use to prove this is the connection between harmonic measure and Riesz transforms, and this estimate that bound from below the Riesz transforms minus, well, it bounds from below the solution of the Riesz transform of an arbitrary, essentially arbitrary measure using the beta 2 coefficients. And this is a joint result that I obtained some years ago with Damian Dombrowski. And that's all. Thank you.